So again, welcome back to the latest lecture session. Again, as is customary, let's have a quick recap of what we have been up to, right? So we were discussing relevant aspects with respect to remediation of contaminated groundwater, right? So due to various sources, either what do we say, spill off, let's say a hazardous waste or toxic waste, or let's say you have what do we say toxic compounds sometimes present in the aquifer itself, sometimes as is the case with arsenic and such, let's say, right? We have a case where the groundwater is contaminated, and we looked at various cases or not cases, pardon me, options to remediate this contaminated groundwater, and some of them are primarily we looked at containment and pump and treat, right? So then we moved on to the relevant passive technique, which is the permeable reactive barrier, which is used widely abroad. Again, I would say that due to lack of transfer of knowledge, let's say, maybe, and also site conditions that are unique to the Indian context, obviously, I guess, right? So it's not as well practiced in India yet, but again, maybe the situation is going to change sooner rather than later. So permeable reactive barriers, so let's have a quick look at what they are about. So as we looked at, let's say this is the ground surface, and I have the contaminated or the contaminant, there's a release here of the contaminant, that permeates through the soil and reaches the groundwater table, and the groundwater is flowing in this direction, let's say. So this particular groundwater is going to come in contact with your hazardous waste here or toxic waste, and let's say now you have a plume here. Let's say this is the side view, I guess, right? So if it's the side view, I should not have had as much vertical dispersion, but anyway, for purpose of understanding, that's fine for now, right? So if we look at pump and treat, which was one of the other options we looked at to remediate the contaminated groundwater, we saw that depending upon the type of contaminant, especially if it's hydrophobic or the non-aqueous, or if there is a presence of non-aqueous phase liquid, we saw that pumping the water out was not a feasible option, right? Because you have the contaminant, what do we say, in equilibrium between 3 or 4, not 4, pardon me, 3 or 2 different phases, right? What are the phases? Obviously groundwater, solid phase, or the adsorbed onto the soil, and also in the NaPl, right? So obviously we did the relevant calculations, and we saw or looked at those cases, let's say, in which let's say the pump and treat is relatively infeasible, right? And so we started looking at PRBs. What are PRBs? Obviously permeable reactive barriers, right? Permeable reactive barriers. So typically, as we mentioned earlier, they are constructed subsurface, right? This is the side view, obviously, and it's permeable. Though we call that a barrier, it's permeable, right? And then the plume, let's say, is going to now flow through this reactive barrier. So you have my reactive media here. I'm going to choose my reactive media based upon the relevant contaminant and this particular plume, right? So and then as we are going to design the relevant PRB in such a way that as the contaminated plume moves through this particular PRB, you are going to have the relevant removal for your to meet your particular regulations or your design, let's say, right? So in this context, we looked at relevant aspects, and we also mentioned that typically zero valent iron is one of the most widely used reactive media, let's say, especially if you have a contaminant that's oxidized, right? So you have an oxidized contaminant. What does that mean? It can accept electrons, right? So in that case, you need an electron donor, which a good what do we say, example of which is zero valent iron, right? So typically we looked at a few aspects, I guess, about zero valent iron, and what are the different pathways by which zero valent iron can bring about the relevant removal or degradation of this relevant contaminant now. So one is the direct path, not direct, let's say the reduction, as in you actually have degradation of the relevant contaminant, right? And the second case was when we looked at, let's say, reduction and also adsorption onto some of the byproducts of this particular iron or zero valent iron being oxidized to Fe3 plus, right? Fe3 plus relatively insoluble, so it's going to precipitate out. So the relevant contaminant can be adsorbed onto this particular Fe3 plus precipitates, I guess, or ferric iron precipitates, pardon me, right? So in that context, you would have both reduction and adsorption, or one, but the balance, I guess, needs to be determined. And third case, let's say we'll have only sorption, right? And this is the case we looked at. So let's say this is your zero valent iron out here, zero valent iron. So as time progresses, let's say you are going to have relevant precipitates on the surface of your particular zero valent iron. I guess we have a figure here that shows that it's continuous, but that won't be the case. You still are going to have, as the reaction proceeds, what are you going to have? You are going to have Fe naught changing to Fe2 plus or Fe3 plus, right? So once it changes to Fe3 plus, let's say, it is going to precipitate out, right? Fe3 plus does not want to stay in the dissolved phase or the aqueous phase. It typically precipitates out and precipitates out on this particular zero valent iron site, right? So I guess that's something that we are seeing here. And again, you are going to now have adsorption of the relevant metal, compound, or such, depending upon the type of compound, obviously, right? So three cases, obviously, or three mechanisms, pardon me: reduction, sorption and reduction, and sorption only. So obviously, if we are looking at the relevant aspects with respect to reduction, I need to know if the relevant reaction or reduction of the relevant contaminant is feasible or not. So one way to look at that is PE, EH naught, or P naught, EH naught, or such, right? These are just going to give you an idea about the reaction feasibility, let's say, right? So I'll move on here. So what are the other reactive media and how can I select them? So these are the treatment materials typically used. Let's say in this column we have the treatment materials, the typical target contaminants. We are going to look at the relationship, obviously, and then status, as in are they in practice or in field demonstration or still in at the laboratory scale. We are going to look at that briefly so that we get an idea about how feasible is the relevant process or mechanism or such, let's say. So as we mentioned, zero valent iron widely used, right? So it's a reducing agent, yes. So obviously reducible metals, and also hydrocarbons or chlorinated solvents, let's say. Hydrocarbons, chlorinated solvents, what is the common relevant aspect here that we need to understand? That they are oxidized contaminants and you can have reduction of those particular compounds, right? And again, as we mentioned, widely practiced. And then other reduced metals, let's say, again instead of zero valent iron, obviously reduced metals, but they might be relatively costlier or have other issues here. Similar to the case of zero valent iron, good, what do we say, good example for or good case of being able to reduce oxidized contaminants. So that's what we have here, hydrocarbons or halocarbons, pardon me, and reducible metals, right? Halocarbons or chlorinated solvents, good example. So but here, as you see, the feasibility is still up in question. That's why we still have it, what we say, mentioned here as field demonstration, I guess, right? As in pilot scale studies have been, what do we say, done, but full scale demonstration or not demonstration, pardon me, they are not yet put into use. So metal couples typically for halocarbons, and again, as we see, only for field demonstrations. Limestone, right? And this is an obvious case. And when are we going to use limestone? Obviously when we want to, what do we say, neutralize the water or such, let's say, right? So obviously good case when you want to, you have acid water or acid mine drainage, and let's say one of the aspects you need to control is the pH. So obviously limestone coming in contact with your acid water, let's say, is going to help neutralize the relevant, what do we say, plume, let's say. And obviously second case is metals, right? And here one aspect is that we need to understand is metals, let's say, they can precipitate out, right? So for precipitating out you need a ligand, let's say, right? And what do we say, so here it's a case of metal requiring a ligand, right? And ligand in this case typically will be either can be OH minus, let's say, right? And typically when would you get that? When you increase the pH and such. So that's one particular way to go about that, or other aspects in limestone, let's say, right? So in that case, again, metals can be precipitated out and acid water can be neutralized. So again, this is in practice, right? In practice, zero valent iron and limestone. So SOP2 agents, as in those agents that have considerable surface area and would are, what do we say, amenable to have or to provide sites for adsorption for the relevant compounds. So typically organics, let's say, which are insoluble or would not want to stay in the aqueous phase or in the groundwater. So let's say now if you have this particular adsorptive agent, let's say, or SOP2 agent, the relevant organic compound in the contaminated plume once it comes in contact with the PRB or the relevant soft agent, will be adsorbed onto the relevant agent here. And metals, let's say they can precipitate out or be adsorbed onto the relevant soft agent. So depending upon the type, obviously I guess we have some in field demonstration, some in practice already. Again, reducing agents, obviously reducible metals and organics, right? And here a relatively unique case as in biological electron acceptors, right? And what's the key here? We have the hydrocarbons here, right? And I guess in this case I just need to point something out that I misspelled it earlier. Here it was not hydrocarbons but halocarbons, as in chlorinated solvents or such, right? Chlorinated solvents obviously are oxidized, hydrocarbons obviously are reduced, right? So if you already have a reduced form of relevant compound, putting in a reducing agent would not work. So obviously that was a misspell here, right? So here it's the oxidized form and here we have the reduced form. So if you have reduced form, what does that mean? You have an electron donor, right? So you have an electron donor here, right? So what do you obviously need? You need an electron acceptor, right? But typically though for petroleum hydrocarbons and such, let's say, you can try to promote, let's say, natural attenuation or degradation by microbes present in that particular soil or such. But for that obviously for that particular natural attenuation to work, what do you need? You need to be able to promote their particular growth, and for their growth what do they need? They need energy, let's say. And how are they going to gain energy now? By promoting relevant redox reactions. And what's the redox reactions that they can promote? This particular oxidation of petroleum hydrocarbon. But the petroleum hydrocarbon is only an electron donor, right? For the redox process to go through, what else do you need? You need an electron acceptor. So in that case, the reactive media can be a electron acceptor or a biological electron acceptor, right? So again in practice and also in field demo. Yes. So quick recap: zero valent iron, a good case for oxidized contaminants such as halocarbons, let's say, right? And reducible metals, and then limestone for acid, water and metals, and then again biological electron acceptors for the reduced compounds, which in this case are hydrocarbons, right? So again let's move forth. So typically again we are going to look at zero valent iron. Again, why is that? Because that's most widely used. Inorganics, let's say, chromium, arsenic, mercury, cadmium, uranium, and nitrate and sulfite, let's say. Nitrate, let's say, NO3 minus can be reduced to NO2 minus and further 2, I guess, right? Chromium, let's say, from +6 oxidation state to +3, pardon me, reduction first and then adsorption, let's say, or chromium in its oxidation state of +3, let's say, is going to precipitate out. And again similar cases with most of these such heavy metals here. And organics, obviously what do we see here? We see a lot of all are halocarbons, mostly anyway. So chlorinated compounds here, right? Chlorinated compounds and so on, right? TNT again, typically where would we come across TNT or such? Let's say when you have, let's say, army ammunition dumps or such, let's say. And typically these ammunition dumps or firing ranges, let's say, that the army has, they have contaminated soil, considerable contaminated soil, because obviously they use the relevant explosives or the relevant area for what do we say, practice out there, right? So obviously you are going to have contaminated soil, and also if you have ammunition dumps, let's say, that have leached or leaked over time, that's one particular case when you can have the relevant soil contaminated by the explosives such as nitroaromatics, right? Again, obviously in such a case, let's say, where they are remarkably what can I say, use the term explosive, right? Taking them off site or treating them and such, relatively expensive options. So in that case, PRB or reducing the relevant compounds by using zero valent iron PRB is a pretty good way to go about it, right? So let's move on. Again, these are the common what we say contaminants typically reduced by zero valent iron, right? So moving on. So before we go further though, we need to be able to decide, let's say, if given what do we say, the conditions that we have, is PRB feasible or not, let's say. So that's what we are going to look at, and that's called the conceptual or developing the conceptual model. Now for that particular case, what do I need to look at? Obviously I need to know the contaminant type, let's say, right? As in if it's an oxidized contaminant, then I'll choose the relevant what do we say, zero valent iron or relevant reduced compound or reducing agent to treat my contaminant. So obviously I need an idea about the contaminant type, And the key aspect is to be able to understand the plume size and distribution, let us say, right. For example, if the plume size, let us say, and the distribution in such a way that it has spread over a large extent of area, let us say, right, and then it does not make sense obviously, or it is not feasible to be able to treat that particular plume, right, at least at the relevant peripheries anyway. You can have it at maybe midway or such, or at strategic locations, let us say, but when the plume size and distribution is way too large, sometimes PRB is, not sometimes, PRB might be infeasible, right. And also let us say plume size and distribution is important because obviously you need to know where to place it, what is the width of my PRB, right, what is the depth of my PRB, and so on, yes. So typically let us say in those cases where the PRB installations have failed, it was not because of, let us say, the PRB failing due to the technical deficiencies, but because the plume size and distribution and many deviations from the estimated distribution were not looked at stringently, let us say. Again, the plume size and distribution was not what we say accurately looked at, and thus people had issues with PRB failing. Why is that? Because the contaminated plume did not go through the PRB but went around the PRB, right. Again, depth of aquifer, the relevant impermeable layer, right, that will give you an idea about again the depth to which your particular PRB needs to be installed, again relevant also to the plume size and distribution. Groundwater flow characteristics, right, obviously you need to know the hydraulic conductivity and the relevant velocity and such, groundwater flow characteristics, pardon me, and groundwater geochemistry, as in are there any other compounds in that particular relevant aquifer, let us say, that can either aid or hinder the relevant reactions that would be promoted in PRB. For example, you have zero valent iron, let us say, and you have water that what do we say has considerable dissolved oxygen, let us say, right. So what is going to happen here? Your water would react with the zero valent iron, or water which is an electron, not water, pardon me, the oxygen which is an electron acceptor will react with zero valent iron which is an electron donor, right. So what does that mean? Let us say the relevant kinetics of your particular reaction or the number of sites available for your particular reaction, let us say, where zero valent iron degrades the relevant contaminant are going to be lesser, right. So in such cases obviously you want to look at groundwater geochemistry, and also let us say with respect to constructability, as in what is the feasibility, let us say, with which at given that particular aquifer characteristics, and also the depth at which you need to construct it, the kind of PRB that would be suitable, can I construct that, yes or no. So these are the aspects obviously, right. But typically it is the plume size and distribution, groundwater flow characteristics, contaminant type, and I guess to some extent groundwater geochemistry that we look at this stage now, right. So in this case obviously to be able to understand whether it is feasible or not, we have the relevant what we say graph here. So here I have decreasing, okay, that is not the right way I guess, okay, here I have the redox potential, right. So in one of the earlier cases when we looked at zero valent iron, we looked at what do we say cases where it would work as what do we say only a reducing agent, and the second case where the process such as adsorption and reduction go hand in hand, and one case where only sorption would be feasible or such. So how do I know, let us say, whether a relevant compound, let us say, can be reduced by this particular zero valent iron or not, or in which cases will this particular zero valent iron based PRB work well, let us say. Obviously what are some of the what we say ranges in which it would not work well? When you have oxygen here, right. So obviously in this zone, let us say, when you have oxygen, obviously you have the relevant EH0 out here, right. So you see that in this zone obviously it is not going to be feasible out here, right. Why is that? Because obviously you have, let us say, a relevant compound here somewhere out here. Let me look at this relevant case once. So here we have the aerobic zone here, as an oxygen would act as the electron acceptor, as you can see here. So let us say if Fe0 goes to Fe2 plus 2 electrons, or Fe0 goes to Fe3 plus 3 electrons, let us say, these electrons are going to be preferentially be what do we say consumed by or accepted by oxygen here, especially obviously as you see that it is an aerobic phase, and EH0 here is greater than, or for O2 anyway, is greater than that for, let us say, the relevant cases where sulfite or sulfate, let us say SO4 2 minus, is being reduced here. So, what does that mean now? Let us say, obviously you know the relevant reaction that would lead to promotion of typically anyway, obviously kinetics is a different aspect. The greater the energy, those reactions, energy release, those reactions would be promoted. So, obviously as you see, let us say in this case, if you have oxygen as an electron acceptor, that would be the first compound that would preferentially react with this electron donor, right. So, in this order you have the preference of the relevant electron acceptors, right. So, what does that mean? So, if oxygen is present and let us say SO4 2 minus is present, right, which one would react with preferentially with 0 valent iron? Oxygen, yes. So, same case with let us say nitrate and so on, right, nitrite, I guess it is nitrite and O2 minus, yes. So, here you have the aerobic zone and anaerobic zone, but typically let us say this is the optimal range for anaerobic dechlorination, and this is where you get the typical EH naught values for most of these chlorinated solvents, let us say, right. So, again the key aspect is if you have a chlorinated solvent and oxygen at relatively high concentration and you have 0 valent iron. So, obviously which one would react with 0 valent iron? Oxygen here, right. So, obviously for optimal removal of these particular chlorinated solvents, you need to have, or you should not have oxygen, right. So, or you need to have the optimal anaerobic conditions. So, that is what we can see here. Again as I mentioned, decreasing amount of energy release during electron transfer, right. So, as I go from here to here, decreasing amount of energy is released, and one metric or you know an idea would be to look at the redox potential here, right. Again let us move on. So, once I am done with the conceptual model, site characterization, let us say now let us say I know that okay it is feasible, or you know I have the relevant information, preliminary information to know that it is feasible, or it as in installation of PRB is feasible, and now I can put in more resources to understand let us say or you know to look into the system in greater detail. So, obviously what do I need to know? I need to know the composition of groundwater, as in what are the different contaminants and concentrations of the contaminants, right. And again plume distribution, let us say, and with greater accuracy, yes. Geochemistry as in pH, dissolved oxygen, calcium, concentration and so on, right. And these are the aspects that I am going to look at. And again stratigraphy, I guess, right, and groundwater flow velocity and direction, but again these are aspects we considered in the conceptual model, but we need them in or you know in greater detail, let us say in this case. Stratigraphy as in you have different strata, right. In the case of what do we say pump and treat, we looked at stratigraphy too, as in we had sand layer, clay layer and so on and so forth. So, again the relevant aspects play a role here, so you need to look at the stratigraphy here too. And obviously what will this help me with? To select the appropriate reactive media, as in from this particular case as in types and concentrations of contaminants, I can select the appropriate reactive media. It will help me to conduct treatability tests again and then design the thickness of the wall, right. So, obviously what am I going to design? I am going to look at let us say the length of the PRB and the height of the PRB, but typically that will be determined by the plume size and distribution, yes. But what will the thickness of the PRB be determined by, right? It will be determined by the kinetics, as in how fast can the reactive media degrade your particular contaminant that is going to flow through your PRB, as in this is the side view and this is my PRB, and let us say if I am looking at the concentration profile here, let us say, right, or let me say this is the thickness and the contaminant is coming in and you know going through, and this is concentration on the y axis and distance or thickness of the PRB here, right. What would you observe? You would observe profile something like this, right. So, by the time it reaches the particular outlet of the PRB, the concentration typically would be relatively less. So, that is my design basically, as in how do I end up with calculating the thickness, right. So, these are the aspects that you know I need to look at to be able to get my design info, yes. So, moving on, I guess we talked about stratigraphy. So, later on maybe a couple of sessions later let us say we are going to look at a particular case study and we are going to come back to that. So, the particular case study is that you have uranium mine tailings, let us say, and I believe they had a uranium mine and the relevant tailings were what we say contaminating the groundwater and sometimes the surface water, I believe, right. So, here they looked at the different strata and such. And why is that obviously important? You need to be able to get an idea about again hydraulic conductivity of the relevant strata and how the groundwater is flowing through that particular media and so on, right. Just a quick example here. Again, what is the case here? You have, this is the side view obviously, and you have these uranium mine tailings, either the runoff, let us say, or the relevant leachate was contaminating either the surface water or the groundwater. And the case that we are going to look at later on is how did the people go about choosing the relevant reactive media, let us say, and how what were the relevant results and such. Yes, we will look at this in greater detail later on. So, obviously for that, again, as I mentioned earlier, you need the potentiometric surface, let us say, as in I need to get an idea about what is it here, water level, right. That is what I mean when I refer to potentiometric contours. So, you have piezometers, let us say, which can help you get this done, let us say. And so, what will this give me an idea about? Let us look at the contours here. So, I have 5358 here, 357 here, 356 here, and so on, right. So, typically let us say I can from these contours estimate the groundwater flow direction, yes. So, from these contours or the relevant measurements, let us say, I can get an idea about or try to get an idea about the groundwater flow direction, yes. So, moving on. So, this is what we see here. So, once people develop that particular contour model, let us say, right, or estimated the contours of the or potentiometric surface, what did we get? So, we see that, like say, depending upon whether we have rainfall or not, in this case we do have rainfall, we have runoff directly, coming in contact with these particular contaminated zones, yes, that is one case obviously, right, and you have the tailing piles here, I guess, evaporation pond, that was another case, yes. So, you have these particular cases, yes, and here you have the groundwater flow, and I believe this was the groundwater flow, yes. So, the case is that you have the stream here, if I am not wrong, you had a stream flowing around here. So, initially let us say the water from the stream flowed into the site, let us say, or the aquifer, groundwater aquifer was recharged by the surface water, what do we say, source, let us say, and that is what you see here, and then the groundwater flow in this direction, and later on again because of the contours, let us say, again from the particular aquifer or groundwater again join the stream here, right. So, what does this mean now, right? So, water from the stream, let us say, can recharge the groundwater, get contaminated here, right, and this zone contaminated here, and then what can happen, it can contaminate a wider area, and as it flows through and again reaches the stream though, right, and now the stream can take the water or the contaminated water over a greater extent, right. So, the case here was that initially let us say the water or the contours were such that the water from the stream, let us say, was recharging the groundwater upstream of the relevant contaminated site, right, and then the groundwater, let us say, was being contaminated at the relevant contaminated sites, right, and then flowing through. During this process, obviously you are going to have the soil contamination, obviously groundwater contamination, and then the key aspect was this particular groundwater, contaminated groundwater was again joining or rejoining the stream, right. In such a case, what would you expect? Again, here that it is the case of transport of the relevant contaminant, in this case uranium, over a remarkably wider extent of area, and thus greater number of people being affected by the relevant contamination, right. So, again the key is that the aspect that I am trying to convey is that you need to be able to understand how water moves. Why is that? Because obviously that typically is how, let us say, or the factor which decides, let us say, the contaminant transport, right. So, that is one aspect. And then the other aspect obviously that we need to look at is, if when we were discussing the relevant previous slide, I mentioned that this was during rainfall or during precipitation, let us say. The key is that you need to be able to understand the relevant flow paths, let us say groundwater flow paths and such, both during the rainy season and non-rainy season. Why is that? We are going to look at the particular case here. So, here let us say this was during the non-rainy season, let us say, non-rainy season, and people estimated the groundwater plume to be in this direction, and based on that they estimated the location of the PRB, designed the PRB and put that in, right. And why is that? They have a river or stream here and they did not want the contaminant to reach this particular stream here, right. So, but the case was they only based their analysis on the non-rainy season, let us see. But as we see here, with time or during the rainy season, what would you see? You would see, let us say, there is a recharge, let us say, right. And now the groundwater flow due to recharge is now no more in this direction, but as you can see it has shifted, right. So, it has shifted towards this direction, thus it does not flow through the PRB and now ends up contaminating the relevant stream, right. So when you take into account the relevant what do we say measurements or such, or you need to get when you are trying to get an idea about the contaminant plume or the groundwater flow direction and such, it is critical that you measure it throughout the year, preferably during, let us say 2 years, let us say, if not 2 years, I guess that is what do we say, that would be erroneous to say so, as in to look at drought and non-drought seasons too, right, and also certainly rainy and non-rainy seasons, right. So that is one particular aspect. And as I mentioned earlier, when people think that PRB failed, but it is not the failure of the PRB, but inaccurate estimation of the direction of the plume, right. So that is one aspect we need to consider. So let us say at this stage, what do I know? I know or have an idea about the concentration of the contaminants, type of contaminants, the plume size and distribution, aquifer characteristics, groundwater flow characteristics, and so on and so forth, right. So now what next, right? And now based on this, I need to now, let us say, take a decision whether I can put in more resources and go for further testing or such. So let us say I have been able to take the decision, as in, let us say I deem it that based on literature or available site conditions that PRB installation is a worthwhile way to go about it, okay, I am willing to spend resources. So what next now? So obviously I need to come or choose the relevant reactive media, right. How do I choose the relevant reactive media? Am I going to put in what do we say, number of what do we say, PRBs in the groundwater and then test it there? Again, that is a costly exercise. So what am I going to do? I am going to choose what do we say, from literature or from experience, many different kinds of reactive media, right. I mean reactive media that would make sense in that particular context of the contaminant, right. And then I am going to conduct tests in the lab, either the batch tests or the column tests, right. And from those batch tests and column tests, I will see, let us say, first from the batch test I will see batch test, right, closed system. I will see, let us say, once the system has reached equilibrium, let us say, or if and when the system has reached equilibrium, those conditions, do they meet my relevant criteria, okay. If they do so, then the column test, as in with respect to time, I need to look at the kinetics too, let us say, right, and the adsorption, desorption or reduction and such. So column tests and such, right, or to also understand when the breakthrough occurs typically, right. But typically breakthrough, you would not want that to happen. Obviously you are going to have a lot of reactive media such that breakthrough does not happen. Breakthrough, let us say in layman's terms, is that if I have PRB here and I have concentration, we just looked at the term breakthrough, let us just try to understand that in the context of PRB. So groundwater is coming in this direction, let us say, right, and is leaving in here, right. So typically let us say the concentration, that profile that you would want is this is the concentration and thickness of the PRB, right. But typically over time you will have exhaustion of your relevant reactive media, they will be exhausted, let us say, right, and then you are going to end up with profiles like this, and you would have a breakthrough here, right, as in the concentration at the inlet is the same as the concentration as the outlet now. But obviously we will design the PRB in such a way that we avoid that, but again these are aspects that you would check. So what do we look at? We look at batch test to see that, let us say, multiple reactive media to see at the equilibrium conditions, are they relevant, is there removal or not, and if there is removal, is there sufficient removal or not. Then obviously column tests, let us say on some of the screened criteria, let us say here I end up with 20, and now after screening I have 5, and then these will help me come up with final screening of the reactive media. And obviously to understand, let us say, the retention times or such, or contaminant half lives, estimate the rate constants and such, right. For example, let us say for some reactive media you will have the rate constant, right, but for some, let us say, you might not, or you might not have the pseudo first order rate constants or such. So how do I get that? I will get them from the column tests. Yes, again when I am talking about rates, but I assume most people have some chemical process based background, but for those people who do not have the background, let me just list that out here, or try to explain that here. Let us say if I have A plus B reacting to form some products, let us say, in this case let us say this is 0 valent iron and this is my relevant contaminant, right. What is the rate of my reaction? It is going to be equal to R is equal to K times, K is the rate constant, right, depends on temperature certainly, times concentration of A times concentration of B, right. So typically concentration of A or the 0 valent iron is so high that you can assume that it is a constant. So what will this transform into? It will transform into K dash times concentration of B. So that is my rate. And what is this K dash? That is my pseudo first order rate constant, as we see here, It looks like it's a second order, or it's supposed to be second order, but it seems like a first order. So that's why we call that particular reaction to be a pseudo first order reaction, right? So again, based on my column test, let's say I will be able to estimate the relevant rate constants. So that will give me an idea about which particular what we say reactive media, what we say brings about the relevant removal relatively faster, right? So those aspects are going to be looked at, and based on these tests, I'll be able to choose my final reactive media that I'm going to place in the groundwater in my PRB, right? Not in the groundwater, pardon me, in the PRB. So I guess I'm running out of time, so I'll end my particular session for now, and we'll move on to the relevant aspects with respect to, let's say, monitoring and more importantly design in the next session, and then we'll move on to looking at the case study in greater detail, right? So, and with that I take leave and thank you.